everyone, welcome to the course on biostatistics and design of experiments. We will continue on the topic of chi-square test. It is a very important test. It is almost like a binomial type of test, fail, pass, yes, no, not and so on actually. So, we can use this for looking at sample versus population. Okay, suppose we have a sample variance of S square and a population variance of sigma square. Okay, we can use this to testing the null hypothesis that the population variance is equal to sigma square. That means we want to say whether the sample comes from the same population. So, when we have a set of samples x1 to xn, we are calculating a mean and a variance, okay, that will call it S square, okay, and then the original the population variance is sigma square, okay. Then we calculate something called the test statistics for the chi-square, which is n minus 1 S square by sigma naught square, okay. Here the degrees of freedom will be n minus 1. So, S square will be the variance for the sample, sigma naught square is the variance of the population, and we are trying to see whether the sample comes from the same population, okay. So, there is another table just like other tables, so we can calculate the table chi-square and then either we reject or accept null hypothesis based on comparing the test statistics with the table value. We can use it for testing goodness of fit. That means you observe something whereas you expect something. So, obviously is the observation is different from your expected or the observation is equal to the expected. So, the test statistics will be like this: observed minus expected square divided by expected sum of summation over k values, okay. So, the null hypothesis here will be observed is equal to expected and the alternate will be observed is not equal to expected, okay. Again we look at the degrees of freedom which will be k minus 1, that is total number of data points, and if the test statistics is greater then the table or critical value we reject the null hypothesis, okay. And then we can also use it for looking at independence. That means we are performing some experiments and in one machine, then we are performing some experiments in another machine. So, the results we get, are they somehow correlated to the machine or they were independent of machine. For example, this happens quite a lot when we are doing some analytical work on say HPLC. I have two HPLC, HPLC 1 and HPLC 2. I get some results in HPLC 1, I get some results in HPLC 2. Now, I want to see whether the results are independent of the machine or the results are dependent on the machine. So, this is a very important type of knowledge, especially in clinical trials. So, that is chi-square test for independence. Again here the test statistics will be observed minus expected square divided by expected, okay. So, what will be the null hypothesis here? The two categorical variables are independent, okay, the two variables are independent of each other, or the alternate hypothesis will be that two categorical variables are related to each other. So, the test statistics will be observed minus expected. So, for example, let us take this problem. We have two machines, each machine makes 3 grades of product, A, B, C are the grades, machine 1, machine 2. These are the observed values 3, 9, 8. That means machine 1 is making 3 of grade A, 9 of grade B and 8 of grade C, whereas we expect 4, 8, 8 from machine 1. Similarly, on machine 2 we see observed is 7, 11, 12, whereas we expect 6, 12, 12. So, the hypothesis of null hypothesis is the grades that it produces are independent on the machine on which they were tested, or the alternate will be the two variables, that is the grades and the machines are correlated with each other. So, we perform this test statistics. So, observed minus expected square divided by expected summation. So, it's let me show you how to do it in Excel. Let us do it on Excel. It is quite simple. So, what do? You put in all the data, okay, we put in all the data and then so this is observed say 3, 9, 8, correspondingly we have 4, 8, 8. Okay, then we have 7, 11, 12, then correspondingly we have 6, 12, 12. Okay, so that is, this is observed, this is expected. So what do we have to do? Observed minus expected, square it divided by expected. So this is equal to this minus this square divided by expected is the second column. Do you understand? So observed minus expected, 3 minus 4 is 1 square divided by expected 1 by 4, that is 0.25. So we do the same thing for all the data. Okay, we do the same thing for all the data and then we add them up. It comes out to be, summation comes out to be 0.625. Okay. So summation of this observed minus expected square divided by expected summation comes to be 0.625. Now let us go to the table. There is a table for critical value for chi-square, just like a table for your T, Z, F and so on. So let us look at say it has got two sided alpha and one sided alpha. So if you are looking at one sided alpha here, so how many experiments are there totally? We have okay, sorry, how many? We have say 3 grades. So the degrees of freedom is 2. We have 2 machines, so degrees of freedom is 1. So 2 into 1 is 2. So the degrees of freedom is equal to 2 in this case. Okay, the degrees of freedom is 2, and then we are going into looking into one sided 95%. So you get it as 5.99 here. Okay, this is the 5.99. So the table value is 5.99. So the test statistics is 0.625. So null hypothesis is valid. What is it? The grades are independent of the machine from which it is manufactured. So it's a very important study. As I said, in clinical trials, samples are analyzed in different HPLCs and from different locations. So I want to know whether the results are independent or you get one set of results if you try it out on one particular HPLC. Okay, so that way is a very useful type of test one needs to perform actually. So this is the table I talked about. So we, for a two sided you have it here, for one sided you have it here. So one sided 95% is here, two sided 95% is here. A denotes the lower boundaries and B denotes the upper boundaries, and this is the degrees of freedom. Okay, so we can use this table for different degrees of freedom, and depending upon one sided 95% or a two sided 95%, we use the corresponding columns here. Okay, especially when you are using only two categories. Okay, there is something called AIDS correction. You need to perform that, especially when you are having a 2 by 2 type of data. That means I have male, female, success, failure. Okay, so male, female is could be in the column, success, failure could be in the row. That is called a 2 by 2 contingency table. That is called a 2 by 2 contingency table. Okay, so in such situations, it is suggested that we do something called AIDS correction. Okay, because chi-square distribution is very continuous. Okay, whereas when we have only 2 by 2, it is almost like an integer. It is almost like a binary, you know, male, female, success, failure, no, yes, sort of thing. So this is especially here. So what we do is we take the absolute value of E minus O, that is expected minus O observed, subtract it by 0.5. It is very simple. Okay, but if it becomes less than 0 when it subtract, then you will take it as 0 only. Okay, do not forget it. So we take the absolute, whether it is E minus 1 or O minus E absolute, we take, subtract 0.5 from that, and then perform the calculation. Okay, and then go ahead, actually that will be the corrected, and after that you square it up and then divide it by E minus O divided by E and so on actually. Okay. Okay, let us look at a problem. So what we do is we subtract 0.5 from the absolute value of E minus O. We will look at a problem in a disease with 40% known mortality. Okay, Okay, so they know that if somebody gets the disease, the probability of them dying is 40%. Now a drug is given to 17 patients and only 3 die. Okay. So can we say the drug is effective? That means generally if somebody gets the disease, 40% of them will die. So 17 patients, the drug was given, a new drug, only 3 died. So can we say this drug to be effective? Okay, so here it is almost like a 2 by 2 data, right? So we have dying, alive. Okay, so 17 people, so we expect 40% of 17 to die, that means 0.4 of 17 to die, 6.8. So how many will be alive? 17 minus 6.8, that is 10.2, but we observed 3, so 14 are alive. So observed is 3 died, 14 alive, expected is 17 into 0.4, 6.8 to die, 10.2 to be alive. So E minus O 3.8, so E minus O, actually we may get it as negative, it does not matter, we put it as 3.8, and so we make a correction here, subtract 0.5, subtract 0.5, then you square it up, then divide by, you square it up, you get 10. So you subtract 0.5, it comes to 3.3, square of 3.3 is 10.89, same thing here, 3.3 square is 10.89, so 10.89 divided by expected, 10.89 divided by expected, so we get 2.67. So for degrees of freedom of 1, 95%, okay, so we see here 3.84, that is your chi-square value. So we cannot reject the null hypothesis, you understand. So we cannot reject the null hypothesis because you get a 3.84 as a table, your statistic test statistics is 2.67, so cannot reject the null hypothesis, okay. So cannot conclude the drug is effective actually from these results. Okay, we can also do by of course we can do the same calculation using Excel or GraphPad also, right. If you remember, we can do it by Excel also or in GraphPad also. Let us try to do it in Excel first, okay. So we have so we expect here 6.8, okay, expect 6.8, whereas 10.2 had it problem, and then we expect 10.2, so observed is 3, observed is 14, okay. So this is expected, we expected 6.8 and 10.2 alive, whereas observed is this much. So can we do it by we have the chi-square test here, okay, chi-square test, chi-test. So we give this range, so we get it as 0.015, okay. So it gives you as 0.015, so if you give this and this, okay. So if you take it as a 95% two sided, then okay, you get it as 0.05. So we can also do it through 2 sample, we can also do using the GraphPad also, we can perform these calculations, okay, using this type of things. So the table, the chi-square, as you know, the chi-square distribution table, okay, as so we have the chi-square test, CHI, so it gives you the range, So, we give the actual range, the expected range, okay. So, it calculates and tells you okay. So, we can use this particular chi-square test also for our calculations, okay. Okay. So, here we say we cannot reject the null hypothesis, so cannot conclude the drug is effective. Okay, let us look at another problem. We of course we can do the same thing using the binomial distribution also, okay. What is the binomial distribution? We have 17 data points and we see 3 of them die, the probability is 0.4, okay. So, the probability is 0.4 and we can do this particular binomial distribution and we can say binom. Okay. So, 3 of them die, that is 3 observed out of the total data of 17, p is 0.4, okay. Then we say either true or false, okay. Point 0, if you give it as a false you get 0.034, if you give it as a true 317.4 true, sorry, binomial distribution 317.4. Okay, so 40%, so I made it as 0.4%, sorry. So, it comes to 0.046. So, according to the binomial distribution we can say that you cannot reject the, I mean we can reject the null hypothesis because the probability comes out to be less than 0.05, but when we perform this type of calculation using chi-square, okay, we end up getting the value much smaller then the table value, the test statistics comes out to be 2.67. Okay. So, the main thing is here we have done a correction for age. If you do not do a age correction, obviously the test statistics will come out to be much larger, okay, because here we have subtracted 0.5. So, the test statistics will come out to be much larger if I do not subtract the age correction, okay, then it may become significant. So, the question is many of the softwares might not do the age correction unless we specifically want to incorporate that actually, and ideally we must include age correction, especially if the data set is very small, like a 2 by 2, this is a 2 by 2 type of contingency, expected out, observed, die, alive, okay. So, that point you need to consider actually. Okay. Now, let us look at another problem. This is a typical 2 by 2 contingency type of situation, okay. So, a study was conducted on a sleep inducing drug and it was compared with placebo. So, a drug was being tested to see whether it induces sleep. So, placebo, drug. Whoever took placebo, 8 of them said they slept early and 65 of them said there is no change. 30 of the people who took drug said they slept early, 42 of the people who took drug said there is no change, okay. So, we have this type of situation. So, it was tested on different groups of people, as you can see the numbers do not add up. So, but with the chi-square distribution does not matter, even if the numbers do not add up, that means 2 sets of samples on which it was tested, and the placebo was given to 73 people, the drug was given to 72 people, right. So, even if the numbers do not add up, we can do still a chi-square test without any problem. So, in this problem what we have is 8 of the people who took a placebo had a early sleep, but 65 of the people who took placebo, they said there is no change, and 30 of the 72 people who took the drug said they had slept early. 42 of the people who took the drug in that 72 lot said there is no change. Okay, so we do not know anything about the expected, we know only about what is observed. So, how do we calculate this? It is quite simple. So, for this one what we do is 73 divided by 145 multiplied by 38. Okay. So, we are doing it the same ratio here, 73 divided by 145. Okay, that is the ratio of people who took placebo out of the total placebo plus drug, and in that 38 said early sleep. So, 73 by 145 into 38, that is the expected early sleep who took placebo, that comes to 19.13. If you want to have the early sleep for drug, what do you do? 72 divided by 145 into 38, understand, 72 divided by 145 into 38, that gives you 18.87, that is the expected for early sleep drug. For here what do you do? 73 divided by 145 into 107. Okay, 73 divided by 145 is the percentage of 145 people who took placebo, and 107 is the set of people who said no change. So, the expected should be 73 by 145 into 107, and for this 72 by 145 into 107. So, that comes to 53.15. So, we have 4 observed and we calculated 4 expected. Okay. This is a 2 by 2 contingency table. So, let us put it in the table once again in the table form. So, from the previous table and then what we calculated here, right. Okay. Now, expected minus observed, what do we do here? Expected minus observed, there are 1, 2, 3, 4, so 4 sets of data for each one of them. Expected minus observed, expected minus observed, expected minus observed, expected minus observed. Okay. Now, we need to do a correction. So, 0.5 subtract, see, as you can see, I take the absolute value and subtract 0.5, take the absolute value and subtract 0.5 reduction, then I square it up, okay, that comes to 113, all these, then divide by expected. So, for each one I divide and then I add up, I get 16.12, okay, I get 16.12. Okay. So, with 16.12 is what I get, and what is my degrees of freedom? Placebo drug. So, 2 categories, that means, so I have 1 degree of freedom, early sleep no change, again degrees of freedom is 1. So, 1 into 1 is 1. So, degrees of freedom here is 1, and for 95% I will get it as 3.84. Okay. So, the statistics chi-square is much larger than the chi-square of the table. So, what I can say is I can reject the null hypothesis. So, the null hypothesis is there is no difference between the drug and the placebo, but I am rejecting the null hypothesis. So, I can say the drug induces early sleep. Okay. So, we can do this problem of course using your Excel, using your graph pad also. Okay. So, if you go to Excel, so what do? We take this 4 data set, so I will say expected minus observed 19.13, 53.86, 18.86, 53.13. Okay, then I go up, observed is 8, 65, 30, 42, sorry. So, 19, 53.8, 19, excuse me. So, 19, 53.86, 18.86, 53.1, 8, 65, 30. So, I can say chi-square test, okay, chi-square test. TST actual, that is observed versus expected. Observed is this, okay, and the expected is this, okay. So, I get a very small p value, okay. So, I reject the null hypothesis, okay. So, this is the observed, this is the expected in this particular problem, okay. So, we can reject the null hypothesis. We can also do it by the GraphPad software. Here we have the chi-square here, okay. So, continue. So, we can do statistical distribution interpreting. So, chi-square comes here, we can do it by continuous distribution. So, here we have the chi-square, give the probability 0.05, the degrees of freedom is 1. So, compute chi-square, so it gives you 3.8415. So, for example, if you look at the table here, okay, if you look at the table, it comes out to be 3.84, okay. So, 16.12 is what you have calculated the test statistics. So, we can reject the null hypothesis in this particular problem, okay. Okay, so we can do using the Excel command called the chi test, or we can use the GraphPad also to calculate the probability, or we can use it for calculating the f value, okay. But it is quite simple to do it manually. We can do this very simply by using a simple Excel, and here please note that we use something called AIDS correction, and when you use an AIDS correction, the expected minus observed goes down by 0.5, okay. Okay, some softwares might not consider AIDS correction, so you may get different, slightly different answers. When you do the AIDS correction, you need to take the absolute value and then subtract 0.5. So, here for example, minus 11.13, we still subtracted 0.5. We made it absolute and then subtracted. When you do the 0.5 subtraction, if the result goes below 0, we should take it as 0. So, remember that. Okay. So, it is very simple to do that, and once you calculate the test statistics, which is a summation of expected minus observed square divided by expected, you compare it with the table, and then you see whether the table value is greater or less than the test statistics. If the table value is greater, then there is no reason for reject the null hypothesis. If the table value is less, then you reject the null hypothesis. So, in this problem, as you can see, the table value is less than the test statistics. So, obviously, we reject the null hypothesis, which is drug and placebo are the same, status quo, that is your null hypothesis, alternate drug induces early sleep. So, we accept the alternate hypothesis. So, I also showed you how to do this calculation using Excel also, okay. So, it is not very difficult for you to do it on Excel, the command is chi test. Okay. So, we will continue on this chi-square distribution in the next class also. Thank you very much.